So, just to give a brief background on what a pulsar is, just in case anyone doesn't know.
I don't.
Giant stars can go through different kind of life cycles. Our star won't go through this life cycle because it's a small star. But eventually, red giant stars can either supernova, create a black hole, or they can turn into a neutron star. And when things, collapse into neutron stars, they leave behind, this super dense core called a neutron star. Basically, it's all the protons and electrons get smushed into neutrons. And it's spinning rapidly fast and emitting a whole bunch of gamma radiation and radio waves. And since it's spinning so fast and emitting all this stuff, we can kind of detect it as it spins by us. So it's kind of like a galactic lighthouse. Like bing, 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 we see all these lights.
Wasn't the first pulsar that we discovered, wasn't that mistaken for an alien trying to communicate with us because it responds in a pattern way, sort of way, and they're like nothing else in space communicates in patterns. Or at least that was what I heard from astronomy, from our astronomy teacher in high school.
I don't remember that, but it very well could be true.
Okay, no, well, continue. Sorry.
Right. So there are millions of pulsars out there, and we've detected thousands already. And so what we started off doing is, well, first it was a friend of mine in my orientation to physics class that mentioned that she's like a junior, and so she's been doing this for a few years, and so she invited me to one of the conferences. So I go in there not expecting much, and she's like, all right, cool, you're on the team now. So I'm like, oh, all right. Didn't really know anything about pulsars at the time. And so she tells us that we're going to have to analyze these things called prep fold plots. And I'm like, okay, doesn't sound too complicated. And she shows pictures of it, and if I had cell connection, I'd show you.
Yeah.
But it's like a big rectangle, and there are like 5 actual data plots on there that look like squiggly lines or filled in dark boxes, or one of them is a whole bunch of colors that change colors as it goes.
It represents the wavelength of light, or
not so much. Every different thing represents something different. Mm-hmm. And so one of the things is called. I probably should have looked this up to remember it because honestly, I forget what the things mean. I just know what they do now.
Okay.
One of them is called a reduced chi-squared. And chi is just a symbol that looks like a K, or an X, my bad. So, I don't know how you get it. I forget that part of the process. But
we learned about chi-squared in statistics, and we didn't learn anything about it either. So
okay,
we didn't pay attention.
well, no, you couldn't explain things in statistics.
Oh, that's
just
true.
Like this thing happens.
This is what it is.
Okay, go ahead.
Well, now that I think about it, I get dm and chi-squared confused. dm basically
Direct
is a
message.
measurement.
Yeah.
Dispersion measurement.
So that way you can get some nudes.
What?
DM me, bro.
Oh, I actually just saw that abbreviation this morning for the first time.
Oh, really?
I literally had never seen
That's
DM
because you don't
before.
use your yik yak stuff.
I guess so. Yeah.
Oh, it's terrible.
Anyway, so there's
back to this.
2 things that I get mixed up: reduced chi-squared and DM. And if my professor would ever possibly by chance listen to this, I'm probably going to get kicked off the team. But the DM is a measurement of how far away something is. And
in distance?
Not
or perceivable
in meters.
Distance?
In DM is its own unit. It ranges from 0 to like hundreds.
Is it like an AU, or is it bigger?
No. It's measured in how many electrons the signal passes through when it gets to us. And so a DM of 0 means it passes through nothing. So it originated from Earth, so it's like a radio signal.
Okay.
Okay.
That makes sense.
A DM of 500 would be something like in a different galaxy.
So,
okay.
So that gives some perspective there. What would be like from Mars?
Oh, I don't...
Like 100? Less than 100?
Well, if
that would be
500
way
is a
less.
different galaxy...
That would be point something.
Point something?
Yeah.
Okay.
Yeah.
So that's all you're doing with this? Is just those things?
Well,
Or
that's
is
what I
there a
was
lot
originally doing. And so you look at these plots, like hundreds of them, and you try to see which of these things look like what could be a pulsar. One of the things is two folds of the best pulse. So when the Earth turns, we have the telescopes that look at the sky and take these things that it thinks is pulses, or pulsars. And so it'll take these pulses, make prep folds out of them, take the 2 best pulses, and fold them over themselves. So we can get like a nice good
like
data set.
Like a symmetrical sort of pulse.
Yeah. The problem is that most of the pulses it sees is either radio interference from Earth or just random crap from space. More often than not, RFI, radio frequency interference.
So it's pretty difficult to find a pulsar.
Yeah, I've looked through over 1,000 plots already. I found one pulsar, but it was already discovered. And so I rediscovered someone else's, and that was upsetting. But so like you look at these different parts of it, and sometimes one piece of the plot, and I'm sure this is very interesting, one piece of the plot will look like a pulsar, and the other part of it won't look like a pulsar, and so you're just sitting there staring at this, plot on the screen, and you're just like, screw it, it's probably not a pulsar, and you just skip it, go on to the next
So why does the professor need students' help with it?
Because it's undergraduate work.
Okay.
It's super easy. Once you learn what it is, it took me a few days just to learn what the whole plot was, and I forgot it already. But I can still read the plots. I still know what to look for. It's super easy. Get any undergraduate to do it.